Hello everyone. I am Peng Lei from Zhejiang University. Today, I will introduce our work about facial geometry and reflectance capture. In this paper, we present a lightweight multi-view capture system with different lighting conditions to generate a topology-consistent facial geometry and high-resolution reflectance texture maps. The captured topology, consistent finer geometry, and high-quality reflectance information can be used to produce a lifelike personalized digital avatar. Facial reconstruction has been widely used in digital character creation, augmented reality, customer applications, Apple Face ID, video editing, and so on. Photorealistic human face modeling is a challenge in computer graphics and computer vision fields. Traditional capturing pipeline has been widely used in film or game industry. However, it is very time-consuming and needs plenty of expensive artist inputs to refine the coarse geometry and reflectance maps manually. A variety of methods have been proposed to reconstruct high-quality facial geometry and high-resolution reflectance. Devivec designed a light stage to capture face from a set of viewpoints under a dense sampling of the incident illumination. The reflectance field of a human face is estimated to generate synthetic images under novel illumination or viewpoints. However, this method can only obtain the specific reflectance from fixed view directions and cannot recover the geometry from the measurement data. The specular reflectance is an important visual cue for the meso-structure of the geometry. In this paper, we propose a lightweight, high-quality face geometry and reflectance capture system. Our method is able to capture a full head geometry with extract ear shape compared to the similar capture system. It allows for a capture system simpler and cheaper than a light stage. This figure shows the recovered high-quality facial geometry and reflectance maps, and two synthetic images rendered under a point light source and an image-based illumination. We build the facial measurement system using 24 Canon 800D cameras and 8 MK14EXT flashlights. The 24 cameras are divided into 8 groups, and each group shares the same lighting condition. The trigger signals of the cameras and the flashlights are generated using an Arduino microcontroller. The subjects sit in the chair with the headrest to keep head being still in the about 100 millisecond capture procedure. The flashlights are modeled as point light source, and their positions and poses can be estimated from the camera parameters. This figure shows the pipeline of our facial geometry and reflectance capture system. The input is the 24 input images captured under different lighting conditions. The digital Emily project is used as the shared template. We first construct the coarse mesh and export the associated camera parameters using the commercial 3D reconstruction software PhotoScan. Rather than trimming away the extraneous surfaces manually, we expect to build a topology-consistent mesh automatically by utilizing the non-rigid mesh deformation techniques. After obtaining the consistent coarse mesh, we adopt the photometric stereo algorithms to calculate the detailed normal maps and material information. Consistent coarse geometry is finally optimized to add more details. Our system consists of two components: geometry recovery based on the stereo reconstruction and reflectance capture based on the photometric stereo, as illustrated in this figure, including dense point cloud reconstruction, facial and ear landmarks, non-rigid deformation, reflectance capture, photometric stereo, highlight removal, diffuse normal and albedo, specular normal and albedo, texture mapping, and geometry optimization. We leverage the facial landmark detector to detect the 276 facial landmarks in the template photographs, and our captured images, the 3D landmarks in the template mesh, and our coarse mesh are then calculated based on the multi-view geometry given the camera parameters. Based on the 2D landmarks, we also divide the template images into different regions, which are then back projected to 3D mesh to obtain 3D regions. Different regions are assigned with different rigid and non-rigid parameters for higher deformation precision. We also implement in our landmarks detector for better non-rigid registration. We adopt the faster RCNN, which is widely used in object detection, as our network architecture, and pre-train it on the COCO dataset. We then fine-tune the detection networks on the ear datasets and some ear images labeled by ourselves. We finally apply the patch-based active appearance model to localize the 55-year landmarks. Due to the existence of noise and incompleteness, we cooperate the as rigid as possible mesh deformation technique with the volumetric Laplacian deformation to obtain a topology consistent facial geometry. The goal is to deform the template mesh to a reconstructed coarse mesh while we use the publicly available digital Emily mesh, texture coordinates, 7 associated photographs and camera parameters as the shear template. We parameterize the mapping function as a 3x3 rotation matrix for each template vertex. We formulate the total energy function as a weighted sum of the 4 energy terms, including the landmark matching term, the matching term, the as rigid as possible term, and the volumetric term. The unknown variable Z indicates the vertex coordinates of the template. After deformation, the landmark matching energy involves a phase and ear landmarks of 2 meshes to guide the registration. The L is the corresponding pairs of 3D landmarks. The matching energy measures how close the deformed template mesh to the target. The as rigid as possible energy term is adopted to keep that the transformations of the neighboring points should be similar as possible to ensure the local rigidity. The volumetric energy term is used to avoid the intersection of the triangles. The tetrahedral mesh is generated using the open-source software TETgeneral. The total energy function is optimized iteratively. Firstly, given the initial guess Z, the local rotations are estimated. Then, the new positions are obtained by fixing rotation. The further optimization is performed by repeating the above 2 steps until the convergence. This figure shows the non-rigid deformation results of different expressions. Our face skin consists of a diffuse component which models the subsurface scattering in the skin and a specular component which measures the reflectance on the oily layer. This figure shows an example of the diffuse and specular separation results. From left to right: original image, diffuse component, specular component. We firstly extract the component without specular reflectance. Assuming the specular color is the same as the light color, we rotate the RGB color of the 3D point P in the visible view I into the SUV, so-called color space, to make the component S aligned to the light color. Then the 2 components U and V perpendicular to the component S contain no specular component. We define the chroma intensity as C. We then calculate the chroma normal using the Lamberton photometric stereo method from the chroma intensity. Due to the soft and smooth property of the chroma normal, the chroma normal is not suitable for constructing detailed facial geometry. The finer geometry can be derived from the specular normal. We leverage the multi-view information to calculate the diffuse and the specular component. We adopt this way to blend RGB color. Let us employ the traditional Lamberton photometric stereo to calculate the chroma normal from the chroma intensities. Photometric stereo is a technique to estimate depth and surface orientation from images of the same view taken from different directions. Theoretically, only 3 directions are sufficient to obtain normals, but to minimize noises inherent in the process, more than minimum number is often required for realistic images. For the specular photometric stereo, we model it using Blin-Fong model. The solution is similar to the Lamberton photometric stereo. After obtaining the specular normal, we use a simple iterative inverse rendering method to solve the unknown roughness parameter M. We calculate the geometry function, Beckmann distribution function, and Schlick-Fresnel term. We relight the point under the known lighting conditions using the specular normal and roughness, and retain the best roughness parameter that produces the maximum photo consistency to the captured images. After obtaining the texture for each view, we then use a texturing mapping method to fuse them into a unified texture maps. The mask is used to discard the inaccurate regions. The coarse geometry is obtained from the multi-view reconstruction, and the detailed normal information can be estimated from the photometric stereo. Finally, we adopt the extracted high-frequency specular normal map to enhance the topology consistent coarse mesh. It reduces the optimization problem to solving a linear system, which can be solved very effectively for large meshes. The optimization procedure consists of 2 steps. We firstly use the measured point positions to correct the normal fields, and then use the linear constraints in a sparse solver to optimize the final positions. This figure shows the comparison of the coarse geometry and the detail face mesh. Left is the coarse topology consistent mesh. Right shows that more details are enhanced into the coarse geometry with mesh optimization. We show the effect of the ear landmarks in the mesh deformation procedure in this figure. The alignment error is a bit larger without the assistance of ear landmarks, compared to the optimization result, which considers the ear landmarks. Due to the incomplete ear landmarks, the inner geometry of the ear is not aligned very well. This figure shows the effectiveness of the volumetric as rigid as possible energy term. In the ear region, the volumetric term prevents the intersection of the triangles. The mesh optimized with a volumetric energy term performs better than the optimized without the volumetric term. The recovered reflectance maps are shown in figure, including the diffuse albedo, diffuse normal, specular normal and roughness. This figure shows the synthetic results. From left to right, facial geometry, 3 synthetic views and zoom in facial details. This figure shows some synthetic renderings under novel high dynamic image-based lighting. The captured facial geometry and reflectance are used to produce photorealistic synthetic images. In this paper, we design a lightweight facial capture system to capture multi-view facial images under different lighting directions. We adopt a non-rigid mesh deformation technique, which leverages the facial and ear landmarks. To align the shared template mesh with the reconstructed mesh, we demonstrate the effectiveness of our recovered texture maps by rendering under several fixed-point light sources and image-based illuminations. Thank you for listening.